This chapter focuses on kinetics. So, in my opinion, this is the hardest chapter in the book. For actually both courses, 161, 162. So this is, if you're having a hard time with this and you have to watch the video a few times, that's fine. Because, like I said, this is the hardest stuff for this level. Of course, it gets more difficult as you go on. And the reason why is it's calculus based. I know calculus is not a prerequisite for this class, but the things we're going to talk about right now are calculus concepts. Here we go into this. Kinetics, how fast is the reaction going? So looking how quickly the chemical reaction is. After this chapter, we don't really care how fast the reaction is going. It just deals with equilibrium. But here, now we're going to talk about how fast things go. And I used to watch the show, gosh, what was it? Mythbusters. And I remember they took some scorpions, they chilled them off, and they put them all over the main characters in the show that they really don't care. Scorpions, if you chill them off, they basically can't move. Lizards do this too. So I remember I was teaching this course, and right before I was going to teach this chapter, I had a gecko in my shower, and so what I did is I got a big glass of ice water, and I poured it on the shower, and the gecko was like going around, and then it was going through the cold water, and it was choo 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 choo. It slowed down, and then I was able to capture the gecko, and then I threw him outside. And I like that because I mean, I don't like having geckos inside my house, but I also, a lot of times when I catch them, they drop their tails, and I always feel bad about that. But I like this case that they're in the shower, so that way, I'll just dump a bunch of cold water on it. Oh, there's a spin. Just dumped a bunch of cold water, and then it's barrel roll again. Then I was able to catch it. Okay, so so kinetics is about the rate, how fast things are going. By rate, we mean, so capital delta, that triangle means change in concentration over change in time. And this is akin to speed. Speed is going to be your change in distance over the change in time, kind of like miles per hour. So if I'm going 55 miles per hour, that means in 1 hour I will drive 55 miles. So that's your speed. But let's talk about chemical reaction instead. So imagine this one here is chemical reaction. Hydrogen plus iodine makes 2 hydrogen iodide. So the rate is the change in the change in the concentration. So these brackets means concentration in moles per liter. So brackets means moles per liter. Change in concentration of hydrogen or change in time, or some second time minus, or second concentration minus first concentration over the change in time there. And if you've studied calculus, you can kind of notice this looks like a derivative, and that's what rate is a derivative. It's a derivative of the concentration. If that doesn't make any sense to you, that's fine. That's just a calculus concept. And change is always final minus initial. And looking again at this chemical reaction, so we're losing reactants, so hydrogen is going in the negative direction, and since it's a 1-to-1 stoichiometric ratio with the iodine, it's moving that in a one direction, and then the rate of accumulation of hydrogen ion, rate of appearance, so rate of disappearance of hydrogen and iodine is equal to 2 of the rate of appearance of hydrogen iodide. So let's do that for this example. Consider this balanced chemical reaction. Hydrogen peroxide plus 3 iodides and 2 acids makes I3 minus and 2 waters. And in the first 10 seconds of the reaction, the concentration of iodine dropped from 1 molar to 0.868 molar. So what is the average rate of this reaction in this time interval? So we're looking at I3 minus. So I minus, so it's final. I guess the average rate of this chemical reaction, the whole one, we're losing iodine. Iodine changes by a factor of minus 1.3, or sorry, it's 0.1 0.32 molar, right? So we're losing, this is the iodine over 10 seconds. So this means that iodine by molarity per second, this is 0. Negative 0.0132 molar per second, and this is the rate of disappearance of I minus 3. I'm sorry, I have 3 I minus, I'm sorry, I have the wrong one. I minus, so the whole reaction, so the thing is though, iodine is disappearing 3 times as fast as the entire chemical reaction, right? Because there's a 3 there. So like if I want to look to see how much money am I going to lose, and if I end up spending $3 a second on something, the whole process though, if I'm losing money 3 times as fast, I'm losing, the whole process is going 1/3 the rate that I'm losing money, if that makes sense. Because the 3 here, what I'm trying to say is the 3 here on the iodine makes iodine disappear 3 times as fast. I like using money examples. So this means the average rate of the reaction, it's going to be 0.0132 divided by 3. And I notice I changed this to a positive because it's just moving forward at this rate. And this is going to be 0.0044. Is that right? 13 divided by 3, that's 4. Yep. And this is molar per second, and this is the whole reaction. This whole reaction is going, the rate of this reaction is going forward at that point, at these average rate over those 10 seconds. Predict the change in hydrogen ion. So the change in hydrogen ion there, it's just going to be minus 2 times the rate. It's going to be minus 2 times the reaction rate. And where am I getting that? Because there's a 2 there in front of the hydrogen, and the negative comes from the fact that hydrogen ion is on the reactant side. So the reactant sides they disappear, then in the negative direction, the products are in the positive direction. So this is going to be minus 0.0088 molars per second. So okay, so why don't you look at this example and think about it. Blood glucose levels drop from 120 milligrams per cubic meter to 110 milligrams per cubic millimeter from noon to 1 p.m. What is the rate of disappearance of glucose? So think about this if you want, but noon to 1 p.m., that's a time of an hour, and 120, 110, we're losing it at this rate there. So hopefully that's an easy one. Okay, so next thing we're talking about are rate laws. Rate laws can only be experimentally determined. So we do not have the knowledge and technology to figure out how to do rate laws yet. We're getting better, but right now this is something that we can only do via experimentation. And I'm just going to start with the simplest equation, reactant A. So reactant A is going to some sort of products. And the rate law is equal to some rate constant, which we find out later is temperature dependence, times the concentration of A raised to some power. And that power, I'm putting in the symbol N, is the reaction order. And that's nice for one product. What about one reactant? What about two? We can have rate is A plus B goes to products. The rate is going to be equal to some rate constant, temperature dependent. A raised to some power, B raised to some other power. So we don't know what that is. So this is next thing we're going to do is talk about what these powers mean. How do we solve them? So zero order rates, reaction rates can be zero order. They cannot depend on the species. So zero order, you're easy to deal with. The rate is constant. So for instance, a process like sublimation. So if you want to look to see if you have something like carbon dioxide or iodine, carbon dioxide, you just need something cooler than ice to have it recondense. But if you are looking at a process like this, if you have a constant heat source, it's just going to go. And it's going to go at a constant rate. First order, so let's talk about first order. This is when the rate is equal to some rate constant times the concentration to the first power. Which means if you double the concentration, you double the rate. And most things, almost everything is first order. And we can make a B first order as well. So nuclear decay, that's first order. Money and finance and investing, interest, this is first order. And most chemical reactions are first order. Second order, this is some rate constant times the concentration A squared, which means if you double the concentration, the rate quadruples. This may happen for some chemical reactions. It's more rare. Things tend to be first order, but there can be second order. And for multiple components, if we have the rate constant to some factor n and m, so run reactant A to the n, reactant B to the m, the overall order is the sum of the exponents. Okay, so if you see here, let's look at this chart here. The y-axis is concentration of the reactant A, and the x-axis is time. So the first line here, we have zero order. That is just a straight line. The rate is constant. The first order is it's actually going to be a parabola, and then the second order is going to be a cubic. You can see they differ. Then if you know your calculus, take the derivative. The zero order is going to be a horizontal line is constant, and the first order is going to be a straight line. The second order is going to be a parabola for the rate. So, all right, how to determine the reaction order. So there's two ways to do it. I'll show you both. It'll be easier to explain it in the second way to do it in an experiment. Rate is equal to some rate constant times concentration of reactant A to some power. So if you look at this one here, the first order, if you double the rate, you double the concentration. So if you notice, for instance, if you put in 2A, the new rate, so if it's first order, you put in 2A, rate is some rate constant times 2A to the first power, and you end up doubling the rate. Already talked about zero order, doesn't change. Second order, if you double the concentration, you quadruple the rate. So here's second order. Throw in 2A for the first concentration, and the squared makes it 4 times the rate. So second order quadruples the rate. Okay, so let's use this to look at an example here to see if we can figure out what the rate law is. So we have reactants going to products. Now, writing this down like this is considered chemistry common sense. You should be able to look at this and then just write a rate constant, one of the reactants, so just whatever reactants you are, and you put them in there and you add a certain number of exponents. So I mean, I guess if you run out of, if it's more than 2, pick something else. N, M, I don't know, O, it looks like 0, so maybe put P. So whatever one works for you. Okay, so how do you do this? Well, you can do it by inspection. So there's a method called inspection. This one here doubles, this one stays the same, this one goes up by a factor of 4. That means that N is 2, and here this one doubles, this one stays the same, this one goes up by a factor of 1, M is 0. So if you can do it by inspection, and you can figure it out that way. That's one way to do it. That's called by inspection. So let's look at doing it in a different way. So we have our rate here. So let me look at this first line, and let me write out rate. This equals 0.0021 molar per second equals some rate constant times the concentration of NO, which is 0.1 to the N power, concentration of carbon monoxide, 0.1 to the M power. And above that, let me write this one. I'll change colors for you. So we have our rates, which is 0.0082 molars per second equals some rate constant, so 0.2 to the N, 0.1 to the M, and I've already drawn a line there. I intend to divide these, so let me get rid of this. So I'm going to divide these, and what happens here, I'll use black, or there we go, black. Molars per second cancel, the rate constants cancel, and the concentration of carbon monoxide cancels, and we get 0.0082 over 0.0021 equals 0.2 to the N, 0.1 to the N. If we do this, we can put 0.2 over 0.1 to the N equals 2 to the N. So how do we solve this? So where we're at right now, we're at 0.0082 over 0.0021. I like to make it easier. I'll say 82 over 21. Multiply both sides by 10,000 equals 2 to the N. Oops. So what we can do is we can take the natural log of both sides. So natural log 82 over 21, quantity, equals n ln 2. If you take the natural log of both sides, that's what that is. And then solve for n. N equals ln 82 over 21, quantity, over the natural log of 2. And if I put that in my calculator, okay, putting those numbers in the calculator, this is what I got. So like I mentioned, it was 2 before, and if I do the same thing, I will find out that the concentration of carbon monoxide is 0 order. So this is where we're at right now. So now we know that our rate is equal to some rate constant times the concentration of NO2 squared. So the next thing we have to do is figure out the rate constant is, and what you do is you pick any line, and I'm going to pick the first one. So we need to figure out what the rate constant is. So rate is equal to 0.0021 molars per second equals a rate constant times the concentration of nitrogen monoxide, 0.1, let me put in the units, molar squared. Okay, so 0.0021 molars per second is equal to a rate constant time, then squared 0.01. This is 0.001. Oh no, too many zeros. 0.01 molar squared, and that means 0.0021 molars per second over 0.01 molar squared equals rate constant equals 0.21 1 over molar seconds, molars times seconds. And what we typically do in this is we write it this way, 0.21 molar minus 1 second minus 1. I'm not sure why we write it this way. I assume it's because of typewriters, because it's easier to write things that way. So now let's write the overall rate law. The rate is equal to 0.0, oh, too many zeros, 0.21 molar minus 1 second minus 1 times the concentration of NO2 squared. So here is the overall rate law. So, okay, so recap on this one. How do you figure it out? You can do it one of two ways. You can do inspection. From inspection, you can figure out that it's second order with NO2 and zero order with CO. Or you can do the long math method that I did here to prove that it is in fact second order. And then after you get the reaction order, you can go and then figure out the rate law. Well, you have to figure out the rate constants from that. Okay, so that's how you solve this one. So why don't you try this one out? So go ahead and take a look at this and think about it, and I will quickly go and solve it. Okay, so if you've gone through this, you can try the inspection method, or you can write out the answer, and you can see here that it's chloroform. This is pretty straightforward. That's CHCl3. That's obviously first ordered. Then the thing that's an issue is the chlorine, Cl2. If you double the concentration, the rate goes up by a factor of 1.42. You can do that by inspection. The square root of 2, I remember it is 1.414. Because partially the sine and cosine of 45 degrees, that's square root of 2 over 2, which is 0.707. So I just have that memorized from the trigonometry. But if you don't have that memorized and you can't do it by inspection, that is totally fine. You can do it the long way, and you can solve it like I've shown here. The 2 to the m is 1.42, and then you take the natural log of both sides, solve for m, and you get 0.5, which is a half. Okay, so do the rate law there. Now I want you to try it out with the rate constant, and it is important to get the units right. So I know I haven't emphasized that, but the units are important. So why don't you try this out, and the rate has already been given for you. Okay, now that you've tried it out, hopefully you picked the line. I picked the first line because I can do this in my head. I didn't need the calculator with the ones. So I wrote the rate. So remember, the rate equals rate constant times CHCl3 chloroform times Cl2. I forgot the 2 here. Cl2. And then, so I wrote that out here in this equation. The square root of 0.01 is 0.1, and then molar. Raising something to the half power, that's the same thing as the square root. So 0.1 molar to the half power, or square root of molar. Sometimes we call it radical molar, so the square root sign is sometimes called radical. So when you multiply something with the same exponent, you can add the exponents. So 0.01 molar times 0.1 molar to the 1/2 power. 1 plus 1/2 is 3 halves. So you have, and the 0.1 times 0.01, that's 1,000th. So rate constant, the rate 0.0035 molars per second is equal to rate constant times 0.001 molar to the 3/2 power. So you divide both sides by 0.001 molar to 3/2 power. Dividing by 1,000th is the same thing as multiplying by 1,000, and the molars, so molar not listed as 1, so 1 1 molar divided by 3/2 molar, so that's 1 minus 3/2 minus 1/2 molar. So we can put that exponent up. Rate constant is 3.5. The molars to the minus 1/2 power, seconds to the minus 1 power. So these units are important, and you will be tested on that. So this usually, don't get discouraged if this doesn't make a lot of sense. Students have a really hard time with this section. If you're getting it, fine, awesome. I'm really happy for you. But this is really heavy in trig math. It's calculus based. Although we're not doing calculus here, I realize that I'm teaching you the concepts without talking about the I have to talk about the calculus, but you don't need calculus to do this. If you understand that speed is miles per hour and your distance is the overall distance with that versus the speed, then you can do this. So, okay. So watch this a few times if you're having a hard time, and if you're really struggling, you can always come and talk to me, email me, come into my office hours, that kind of thing. Okay? So we will continue with next section.